So I'm going to open up with talking a little bit about engine start systems in general. So this particular image came from Caterpillar. It kind of shows a very complicated system. There's a lot involved to think about when you're implementing an engine start system. There's ventilation, power distribution, all kind of things. But what we're going to focus on today primarily is just going to be the battery charger and the battery portion of the system. Here's a typical generator. This one in particular would be approximately 1000 kVA. So looking at some of the parts here, and again, I don't want to get too much involved in the rest of the generator itself, but it's a good idea to be able to identify some of the major parts, such as the radiator, intercooler, the diesel engine, turbos on the exhaust. This portion is the generator, which is actually an alternator, and most popular in this market segment would be a 4-pole that would be operating at 1800 RPM. The HMI, which is the human-machine interface, this is where the engine controller is. Very popular in today's generators. It would have a Modbus as well as a CAN SAE J1939 interface. This would be the largest portion of the standing load on the DC system. In fact, older generator systems that have some basic analog controls, there's almost no DC drain on the charger and the battery system. We're going to talk in particular a little bit about the engine starter, as that is one of the key components in how the DC system performs. So let's look at the total DC system. Starting with a USC battery charger. What would be typical in this class would be 2 series, 2 parallel 8D batteries. Each one of these are 1400 co-cranking amps. When you wire them in series, the co-cranking amp stays the same, but the voltage grows to 24 volts. But being that there's 2 in parallel, now we have a 24 volt system that's capable of 2800 co-cranking amps. Like I said, that'd be typical for a generator approximately this size. So this DC bus, almost exclusively in the marketplace, this will be a negative ground system. In this size class of generator, you may have a redundant starter. This is kind of close to the borderline. Quite often there may or may not be an engine alternator for battery charging, and that would also be tied to the bus if it's there as well. So looking closer at the engine starting system and focusing on the starter, you can kind of see from the graphic over here, as the solenoid up on top is being energized, it closes the contacts over here, which allows current to flow to the winding on the motor. So also you notice this cantilever lever. So as the contactor pulls in, it is drawing the motor such that the pinion can engage the flywheel, and that's what actually spins the engine over in order to build compression in order to get the engine started. This is no different than the starter inside your average automobile. It's only bigger. So looking at this, we're going to talk a little bit about how the current draw and as well as the voltage fluctuation on the DC bus relative to engine starting. You're going to hear us talk about this term from NFPA 110 called 315s. So in NFPA 110, and looking at a level 1 system, and taking an example system of like 1000 kVA, that'd be approximately a 30-liter generator. NFPA 110 will ask that when sizing the battery, that it is capable of producing 15-second cranks that also have 15 seconds of rest in between. So what that means is that the battery must have sufficient energy to be able to accomplish that many cranks, but it also must have sufficient power in order to deliver the starting current. So let's look at this in terms of breakaway current. So again, the image up on top, that is the starter current, how much current it's drawing from the battery. And as we all know, Ohm's law, due to internal resistance and losses on the battery, as you start pulling a lot of current through, it's going to give you an instantaneous voltage drop. So that's kind of why the voltage is kind of a reflection of the load current. So this first portion over here is called the breakaway current. You'll notice that it's a fast rising edge, and in this instance it gets to over 1400 amps. And it's very narrow. Typically this is there and gone in less than 700 milliseconds. So what constitutes this high leading edge is building flux in the motor and overcoming the beginning inertia of turning over that engine. So you'll notice when there's a high spike of current, again, there's a large momentary dip in the voltage on the battery system. So the next portion is considered a rolling current, or some people call it cranking current. So this is while the starter is actually turning the engine, but before you've actually accomplished diesel ignition. So the controller that's inside the generator will normally limit this time to somewhere in the vicinity of 10 seconds or maybe 15 seconds. The reason that we go for 315s is because NFPA 110 is going to require that's how much energy you should have in a level 1 system. So some factors that affect this would be the engine displacement, the temperature, the oil viscosity. All these other factors affect what this rolling or cranking current will actually be. And you'll notice that there's a voltage dip during the same period of time. Again, the load voltage, or the battery voltage, I should say, is a reflection of the total load current. So here's another view of this comes from the EGSA, and so this is while starting. The EGSA has a different recommendation for these periods. So B being the initial breakaway period, on a 24 volt system, they want to see that the battery voltage stays above 12 volts, even for that momentary dip. During the cranking section, or the rolling current section, the battery must stay above 18 volts. And as you can imagine, if we're not talking about a 12 volt DC system, or I'm sorry, not a 24, but we're talking about a 12 volt, then these voltages would be cut in half. This portion over to the right is after the engine actually starts, and you'll notice that the RPM curves up, because that's when the engine is actually getting itself going. So the engine starts, the amps drop down, volts kind of start climbing back up. So let's talk about this. What happens if your delta V, your voltage drop, is too large? Well, under certain circumstances, you might be hindering the ability to crank the engine. The EGSA only has recommendations against the cranking requirement, but your engine ECM or even the switchgear that might be operated by a larger generator could be affected by this momentary dip of voltage. So that's why it's very important that to look at sizing the system properly and also maintaining your system. Because if the cold cranking amp rating of the battery is too small, you'll have too large of a voltage dip and you could encounter a problem. If the battery internal resistance is high because it's aged or it hasn't been taken care of, you'll have excessive voltage drop and you may start to compromise these components. Same if the wire is loose or corroded. Either way, you could run into a scenario. Here's an example. Let's say if you had a momentary dip that was severe enough, you could drop out the ECM, the engine control module. And if that happens while cranking, it's going to interrupt the fuel pump, and that's going to prevent the start. And that's a bad day, because now you're forced to reset on the system, and you could try over and over again and never get her started. So that's why paying attention to the total voltage drop is so important on an engine start system. So we're going to throw around these terms, such as energy and power. So I'm going to spend some time explaining this because it's going to come up again later in our presentation. So let's look at two batteries. Well, you say, Rich, these are buckets. Well, they're the same as a battery. Guess what? So these have the same amp hour rating because they're the same size bucket, they have the same volume of fluid. They have the same voltage because they have the same atmospheric pressure and we're in the same gravity. So what makes them different? The one on the left has a low cold cranking amp rating, the one on the right has a high cold cranking amp rating. So the reason for that is because, as you can all imagine, with a larger pipe, larger valve, the rate at which water can flow, in terms of water flow per second, you can flow a lot more water. You can empty this bucket much quicker. This means that there's less resistance to the flow of water. So same thing as a battery. When there's lower internal resistance of the battery, you have less impeding the flow of current, so you'll have less voltage drop on the battery. So batteries that you'll find specifically for engine start have less internal resistance, which gives them a higher cold cranking rating than for a given amp hour, as opposed to a long duration battery. So let's look at where we have the same power, but different energy. So again, we go back to our bucket analogy. The amp hour rating is different because the volume of fluid is different. The one with the larger volume has a larger amp hour rating. You have more available water in the bucket. So they have the same voltage because the atmospheric pressure and the gravity is the same, but the current flow, because this pipe has the same resistance, it will limit the volume of water in terms of flow per second. And I know you say, well, wow, Rich, is current really a rate such as a quantity per second? Well, absolutely, because an ampere is related to coulombs per second. So it really is a rate. So keep this in mind, the analogy of discussing power versus energy. Later on in the presentation, we'll bring it up again when we talk about the HCAP versus supercap. So let's talk a little bit about batteries for the system. What's far and away most common in this market segment is a lead acid battery. I got PB here for the lead. So the lead acid battery, it's rated in cold cranking amps, but typically not associated with an amp hour rating. So that can cause some confusion. They're normally in a BCI group size, similar to the batteries that are under the hood of your car. Those are all different group sizes. So what they don't give you in this market is independent sizing in terms of how many cold cranking amps you generally need for an application. So let's look at this in terms of the other battery, NiCad. So if you really look at these, they're polar opposites of each other. The lead is rated in cold cranking, but not in amp hour, yet on the NiCads, it's just the opposite. It's rated in amp hours and not cold cranking amps. These are grouped together in a monoblock. These are normally 1.2 volt individual jars. There's no sizing guidance for the lead, but there is a lot of sizing guidance from other standards such as IEEE 1115 from SAFT, ALCAD, HOPICA. A lot of other guys have sizing tools available. The leads will normally need to be replaced 2-3 years per NFPA, but the NiCads, they'll last a long time, 20 years, plus have a wider temperature range. But the thing with the NiCad is they're expensive and they're difficult to recycle. So a lot of people win out with the lead acid battery because they're cheap and they're easy to replace. And when we say recyclable, lead acid battery is actually 99% recyclable. So let's look at sizing a system. On a lead acid battery, again, they're generally sized and rated in cold cranking amps, not rated in amp hours. So cold cranking amps, you should be thinking, is synonymous with power. And amp hour rating, how much water is in the bucket, is synonymous with how much energy is available. So engine starts, they really don't consume a lot of amp hours. In fact, we went to go test a larger 50-liter diesel engine system that was 1500 kVA. It really only consumed about 6 amp hours. I mean, we're not talking a lot of energy. What we need is power. So quite often 2 parallel strings are used to meet the cranking ampacity, and they're not really sized in for redundancy. They're really designed in for design margin. So the typical battery sizing that we would use in other stationary markets, such as in utilities, substations, oil gas applications, well, those are energy applications, so those are sized in amp hours, and you would normally go through this formula. This is how the Marche sizes, according to IEEE 946. But because you don't have an amp hour rating, you really can't use this system. So cold cranking is a really nice system because it gives you the worst case cranking performance of a new battery. The battery that you choose and select for the system must meet or exceed the generator's requirements. You really can't have too large of a cold cranking amp rating on an engine start application. So let's look at that. Cold cranking amps. So as defined by the SAE, it's the amount of current that a 12-volt battery can deliver at 0 degrees Fahrenheit for 30 seconds while maintaining at least 7.2 volts on the terminals. And by the way, this battery has been saturated at 0 degrees Fahrenheit for at least 24 hours ahead of the test. So this allows you to put on a very heavy load. This really tells you how the battery is going to perform when it's cold and when it's being stressed with a high dynamic current, such as starting the engine. So let's look at totally sizing up a system. So I took a snip from a 1250 kVA generator, and you can ask around for some independent advice, and here's what one old timer gave me. He said, select the smallest battery by cold cranking amps that meets the generator spec. So looking at this, they're asking for 2, which actually is 2 in series, because the 12 volt BCI batteries, well, they're 12 volts, and this is a 24 volt system. So they want 1100 cold cranking amps, and they want it to be an AGM. So we look up on our data sheet and we find, lo and behold, here's a 4D battery that meets the cranking requirement. So after you've done step 1, you go to step 2 and say use 2 parallel strings. That gives you, it's not so much for redundancy, but it's there to help cover other terms like battery aging, the manufacturing tolerance from one battery to another, possibly operating lower than 0 degrees Fahrenheit, adjustments for altitude or other engineering margins. So this is really one of the reasons that you end up seeing 2 parallel strings. So now that we've sized the battery, how do we work on the charger? So UL 1236, here's a snippet. I just love this one. Within UL, they want you to be able to recharge the battery to 100% of the battery's amp hour rating within 24 hours. But the problem is, the batteries in this market segment, they're not rated in amp hours. You gotta follow the standards anyways. NFPA 110, they say something kind of similar, but level 1 recharge, they want 100% returned in 24 hours. Or if it's a level 2 application, you can use a smaller charger that would return it in 36 hours. But although NFPA 110 doesn't specify amp hours, they imply that they want 100% restored. So working with the IEEE, there's a chart that we can make here that correlates the minimum charger size in amps on the left column versus the cold cranking amp rating on the right. And it's not a direct perfect correlation. This is just one of those tables that was assembled from some available tests on a lot of available batteries. So if you have a standing load, you should add that to the result here. So let's go through an example. Let's say I want 2 parallel 850 cold cranking amp AGM battery strings that has a 3 amp standing load. So I would first look up and say, well, 850 amps, that's right over here. That gets me to a 7 amp charger. So I've got 2 of them, so I need 14 amp charger. So then I have to add my 3 amp standing load, so we get 17 amps. Well, we don't have a 17 amp charger available, so we round up to 20 amps. So data on this table was sourced from the draft version of IEEE P2685, which is the recommended practice for energy storage for stationary engine starting systems.